Okay, welcome back, folks. So this is going to be our first week back here in person after the mid-semester break and a few other things. So today we're going to solve lab exercise 5. We're going to be introduced to it and we're going to solve it. The actual solution for this is like 3 lines of code. I'm going to stretch it out to be like 6 lines of code, okay? But it's actually really all about understanding. So I want you guys to make sure that you're here, you're present, you're thinking, and you're participating in the discussion here to really see what we're doing here, because it's the thought process is very important, that we go through the thought process, and that you see the way that you're supposed to solve problems like this. Okay, that's the key skill here. That's what's going to make you different from a robot. You're going to need to be able to solve problems you don't know how to solve. You're going to need to be able to come up with new solutions. You're going to need to be creative, and if you can't do that, then you will be out of a job very quickly. Even in a world without the the AI stuff like that, it's not really a big deal actually. But a world without that, you still have to be able to adapt, because guess what? The technology is advancing very quickly. 10 years ago, if you studied programming 10 years ago, you would still have to learn brand new stuff, now, right now. You'd have to completely change your understanding of the tech world, right? You have to stay up to date.
If you're in web development, it's even worse.
Say again?
I said web dev is even worse.
Oh. Yeah.
Your whole lesson for like this semester is going to change in like 3 years. So.
It could. No. This lesson is physics. The physics will stay the same.
Okay.
The way that we do them will change sometimes. Like I've used several different frameworks to teach this class, several different things. We've done this in many different ways, right? But the fundamental part that will stay is the math and the physics, right? That will stay. And that's what I was able to keep. I had to throw away other parts of the course before, yes, but not the actual math and the physics, because luckily those don't change on us every couple of years. We don't get like a patch notes that change how gravity works.
All of a sudden things get lighter.
Yeah. Anyway, so this is about making objects solid. Lab exercise 5 is when 2 objects touch, they don't phase through each other. Wow. Amazing. We have to make this.
Just asking.
Yes.
I've done something similar to. Isn't the key to like making the illusion of physical objects is that you just have to tell it, do not go past like this plot. Let's say you have a wall.
Sort of.
And then you just tell it, listen, if you go past this wall or you go past -x whatever, then you just go backward.
Yep, we're gonna do something that dumb because that's how it works. So game physics work in frames, 1 frame at a time. So here's 2 objects. Here's what happens now. Right now, this is what happens. You have like 2 objects, they're heading towards each other. Okay, A is going towards B. This is frame 2, frame 3, frame 4, frame 5. Okay, they're overlapping. We, at this point, should be able to detect that they're overlapping. By lab exercise 4, we can tell the part of the goal of the exercise was to make them turn red when they overlap. Right, great. Then they will just continue. Next frame, next frame, next frame, just like that. Okay? What we want to do now is this. Frame 1, frame 2, frame 3, frame 4. We detect that they've overlapped. We can't stop them from overlapping because it's discrete. Because this simulation happens in frames. But this frame, we detect that they're overlapping, we can move them back. Yeah. So we can do one of several things. If our goal is to make them not overlap, One way I could do that is this.
Check like I have a thing on.
I could just randomly put it somewhere else. That's a solution. Not a good one. Not intuitive. Does not look like real physics. Okay. Okay, another one is before I move it, I could check if there's something in front of it and then say, don't move forward. Yeah, but then something weird will happen. It'll be doing something like this. And then they'll like hover apart from each other. Because again, the game only moves in frames, right? Like objects only move in fixed intervals. We're teleporting objects every frame. There is no in-between frames. If we want to make that, we still have to make that happen. Okay. So what else can we do? We've detected they are overlapping. What would be reasonable? Maybe like that?
Yeah.
That's
That
pretty.
would be the idea.
That's pretty reasonable. You know, or like this. Each one goes away a little bit. That's pretty reasonable.
So on like magnets, if they get like too close to each other, then they go back, they move.
Except that it's not that they're close to each other. They're just literally phasing through each other, and then we're telling them, okay, move away. Don't do that. Okay, so that's what we're gonna do. When we find this situation, we are going to ask, are they overlapping? Yes, we did that already. If you guys remember, we can do that really easily, actually. Comparing the distance between them against the radii, that stuff. Now, we're actually gonna ask, how much are they overlapping by? That's kind of one of the main differences that we're gonna do now. We're just gonna find out how much do they overlap. Okay, that's it. Because we have a few different variables here, right? Here, let me make these bigger so that I have more room to play with here. So this is overlap. Okay, that's the overlap. That's how much they overlap by. Okay, great. Now radii. Let me do radius. That's radius. And that's another radius. Okay? And then as well, there's a distance. I'll just call that D. Right? These are the variables we've been dealing with, except for overlap. Overlap is new. Everything else, radius, distance, we dealt with that already. Okay, so now you could say, all right, how much we should move these by, maybe it depends on their mass or depends on their velocities and stuff like that. We could, but actually we're gonna get to that at a later point. We're not actually getting to that yet. And a video game still needs to be able to handle this situation even without variables like mass and velocity or any of those things involved. Because it's very often that this situation will happen without any physics being involved. Like literally, we have collision detection and response, but we also keep that separate from all of this physics and kinematics and stuff like that. Because some video games, you want to have collision detection and response, but you don't want to have bouncing and all of these fancy kinematics going on at the same time. This situation can happen out of the blue with no prior context, with no understanding of any velocity, like these velocities are both 0. This situation can happen in a video game very easily, very often, when you spawn an object. So player spawns, they're partially overlapping a column. What should happen? There's no velocity either way. You can't make the player bounce off the wall or something like that. That's not a thing that you're gonna do. So you still have to be able to deal with this problem. Okay? Or two objects spawn really close together. Oftentimes, if you're spawning bad guys or if you're spawning objects like items or something like that, you're gonna spawn them in the same place or really close together. And you want them to be able to handle that. If you spawn them in the same place, then they need to be able to sort themselves out and look reasonable to a player. after one frame. So that's what we need.
Also trying to like include the actual physics when you separating them might add so much like unnecessary calculations to them.
It's going to be a lot more work to do all the kinematic stuff.
Yeah.
And we will get to that in lab exercise 7. Okay? So lab exercise 7, we will do that. But we need to do this first. And actually, even when we do that in lab exercise 7, we take into account velocity and momentum. Okay? Velocity and mass makes momentum. We take into account momentum of these objects. We are still going to need to actually solve this problem where they're overlapping. We're going to need both. We're actually going to need both. Because with game physics, it is frame by frame. We have this situation, and then immediately next frame we have this situation. Panic. We have to deal with it. Okay, so given this, you actually might be able to intuit how much this overlap is, and how you might calculate that. So far, we've only done radius minus distance to figure out, you know, if these objects are overlapping. We did some code that looks similar to, looks something like this. If the sum of the two radii is greater than the distance, hang on, there we go. If the sum of the two radii together, added together, is greater than the distance, then they are overlapping. Or you could say if the distance is less than the sum of the two radii, they're overlapping. Otherwise, they're not overlapping. Okay. But we need more. We can't just say true or false. Now we need to do something. The amount we need to move these depends on that overlap. It's exactly this overlap. So what is that? How could you calculate that? Overlap equals what? Where's where the overlap started?
Since it's frames, it didn't start like it just happened automatically.
This is just, you have no context. This is what you are given now. That's how the computer has as well. The computer has no context. The computer doesn't understand anything. Yes? Yeah, guys, just look at these. That's why I drew pictures. That's why I made this thing, so you can look at the pictures. So you can take these and move them around. That's why you need to do this when solving problems.
Distance minus the radius. Because I told me to move it.
That's fine. You can do that. Look, okay. We have something going on here. This is a dotted line, so it's kind of hard to read sometimes. Oh, I pushed it too far to that side. Look at that.
So, the two radius together plus the distance plus the overlap are the same. Wait,
They are.
oh wow.
What? Geometry.
It's not a sphere, but it's a sphere like.
Yeah. This is why you gotta draw pictures when you're coding, guys. You need to draw pictures. So how could we calculate this overlap? What are the variables we know? We know this radius of B. We know radius of A. We know distance. We did that before, right? Yes. How do I calculate it? How do I finish this? Okay, yeah. A dot R plus B dot R minus D. Right? Yeah. These two, positive number, Positive number. Yeah. Yeah, I'll take that. Sure.
Actually, that makes sense because you have both of the circles have their own radiuses, and then you just need to, once it's overlapping, you use the subtraction to see, okay, how much of the circles are overlapping with each other.
Here's something we need to do. It seems to make sense, but when something seems to make sense, like let's pretend that you're not hearing it from me, right? You're trying to figure it out yourself, right? You need to test your assumptions. So let's make several cases and see if this works in those several cases, okay? We will often, when solving problems like this in computer science and in math and lots of ways, you need to basically look at all of the different possible cases that could occur. So let's try and create samples of all of the cases that could occur and hopefully prove that. There's a few different ways you can prove things, right? Like one way you can prove something is you can prove that that in every case it's true, it works. You can also prove that if it wasn't true, there would be something that doesn't make sense. A contradiction. Okay, and you can also kind of just have a bunch of examples and be like, yeah, it works in all these cases, so it's probably true. We're going to do that. We're going to do that. We're not going to do the most secure proof, but you will be able to, you can do an actual proof of this. Anyway, we're just going to do this the easy, dumb way. Okay, so does it work in this case? Does it work in, well, we already have that case over there, so hang on. Let me put these in order. So here's one case where they're not touching at all, absolutely nothing. Absolutely no reason for anything to be going on. Here's another case where they are going to be touching, but just very slightly, or just like on the edge. So they're touching, but not overlapping, right? And then let's make maybe one more case where they're just on top of each other.
It's like test-driven development.
Yeah. Anything else we might need? Maybe like this? I don't know. You could make a few different cases. Oh, this seems like this would cause a lot of problems. So I'm going to use this case.
Does it even matter how far which side the inner circle is?
No, it doesn't matter which side because everything we've been doing here is regardless of direction. None of these are vectors. So we do know that we don't need to make up a case like this and then say, oh, what if it was like that? We don't need to do that. Because we can look at, say, okay, all of these cases, this works if they were in any orientation. This is just about the distance because these are all scalars. None of these are vectors. The direction doesn't matter for this problem. Good question. Cool. So does this work here? What are we going to get? Honestly, what would we get? No, you would not get NA.
Like non-applicable?
No, this math works. No, you would not get NA. Don't just assume. Actually run it through. You have an actual distance. You have actual radius. Yes? You are going off vibe. Don't go off vibe. Okay? Don't trust your instincts. No. Here, what can we say about the variables? Look, see, we have A dot R, B dot R, overlap, and D, overlap. Okay, what can we say about D in this case? It's greater than the two radii. Yeah. So we can definitely say D is greater than eta r plus beta r. So then if D is greater than, if this right side is greater than this left side, it would get a negative number. Yeah, not 0, negative number. It's the opposite of what you said.
It's the same logic, so.
Something close enough. Good enough. Less than 0. So this would be less than 0. Okay. What about this? Again, think about these variables. Is D greater than the two radii together? D is equal to the sum of the radii. I'm not gonna be typing this every time. Sorry guys. I'm just gonna. You get it, right? Yeah. Good.
Yeah.
Good. This is being recorded, yes. At least I think so. Hope so.
Check.
Yeah, it's, it is.
Don't trust your vibes.
It is. It is, but I don't have to. So you gotta pay attention. Okay. So D equals sum of rate. So what is overlap going to be in this case? Oh yeah. Yeah, because if we apply this formula here, it's going to be 0. Cool. All right. This case, yeah, okay, it's some number positive. In this case, D is less than eta r plus beta r, right? So it's going to be positive. Greater than 0. Any positive number? Could it be like infinity? Could it be like positive a million? Let's do the other case over here, and maybe that'll help us with this one. What if we apply this here? Oh gosh. So distance is 0. Overlap is the two radii minus 0. So it's just the two radii together. Does that seem reasonable?
No, because the radii are overlapping. So wouldn't it just
So okay, how much should we move this by? Do we need to move this by 1 radius?
By the radius combined.
Oh yeah, we need to move it by the radius combined. So is overlap incorrect? Let's see, how much do we need to move this by? Just gonna stick these here. What if we move it by the sum of the radii? Wait, it worked! What? They're right on, okay, yeah, they're overlapping, but if we move it by only 1, we'll end up with the center on the edge here. We have to move it by both.
Does this only happen because like an inner circle was like right smack dab in the middle of the big circle?
No.
If it was like fully contained, at least it would still cause the same problem.
Oh, let's do one more. Okay, because we were interested. Let's do one more case. Like this. In this case exactly, what is the amount of overlap?
so now the overlap is
The distance is what?
0.
No.
The distance is
The distance is the
radius of B.
No, not the radius of B.
Okay.
Because we're counting the distance between the centers of the circles.
AR.
So overlap is equal to B radius? Okay, let's try that. Are we just guessing?
Didn't physics have a lot of guessing to get to where it was? Like they had to guess how things work?
Not all.
You still have to move it by both of them combined.
Look at this. I move it by, if I move this by 1 radius, the radius of, what did we say it was? B radius? Okay, I'm going to move it by that. Oh. Huh.
But I think the B is missing some of
You think what is missing?
the radius wasn't like complete, it was like going all the way for B.
I'm not sure. I'm not sure what we mean by that, to be honest. Okay. But question is, does this still apply? Does this formula still hold? The one we've been using, is it still correct?
Yes.
Algebra guys. Like if you rearrange these, if you solve for D, in this case, would you get A dot R?
You would get A dot R plus, no,
Plus B, plus B.
Hmm.
minus, yeah, it's E in this case.
We have made the assumption that this equation works. We hope it does. Probably does because I'm talking about it for a long time.
Yes. It's,
But we need to see why.
well, because if overlaps equals the radius of B, then it would just be radius of B. Radius of B.
Yeah, B dot R equals, if we sub these in, like, does it make sense?
Yeah.
A dot R plus B dot R minus A dot R. Does that make sense? Oh, absolutely. It does equal. We just said B dot R equals B dot R. That's all we said.
Yeah.
It's good. It's good. It works, guys. Isn't that amazing? And this guy right here, when D was 0, and overlap is the sum of the two radii, right? That makes sense. Z0, sum of the two radii. Yeah, frick. To move these apart from each other, you have to move by the radius of one, and then the radius of the other. Oops. That total distance, these two add together. So we can solve it algebraically, and we can solve it just geometrically by making these blocks and then moving them around with using this tool, which is nice, you know. You could solve this by making a bunch of sticks, like of a certain length, drawing circles with those sticks, you know, on the ground. You know, you could do this stickman style or like caveman style, which is neat. This looks like, you guys know that scene where they're locking on to Alderaan with a Death Star? That's what it looks like. Anyway, so we have this number overlap. We have this number which is going to be negative in this case, 0 in this case, positive in this case, positive in this case, more positive, and then it can't be more positive than this, right? Because if we move it as far enough the other way, then what have we just created? We've just created this case, but rotated. So we've looked at every possible case, actually. We've actually looked at every possible case. There's no other situation here that we haven't solved. Look at that. 1, 2, 3, 4, 5. Easy. Sometimes you can actually do it like that. Beautiful. So we know how much we need to move these apart from each other. Now we need to know what direction. Can anyone tell me what direction that might need to be? If these are rotated in any which way, right, we need to be able to handle any direction this might be.
Some kind of normalized vector.
Some kind of normalized vector, okay. Which way does it point? So let's say, in this case, which way should we move these apart? Should I move them to the left? Should I move them up and down? What would be reasonable is if I move them by the shortest possible distance. If I know nothing about what's going on, I would say I should move them by the shortest possible distance. So what I'm going to look for is how lazy can I be, you know? What is the minimum amount of work that we can do to move these apart from each other? And that's pretty reasonable. We will call this the minimum translation vector. Okay? So this is a word we might use in computer collision detection and response. Okay? Minimum translation vector. So the minimum translation vector here, what would the shortest distance be that I could move these? Or the shortest direction? This way. Right? Over here, what would the shortest direction be? This way. We're not going to move it up. We're not going to move it down. We're not going to move it like any diagonal here either. It's exactly this way. How could you get that direction? The information that we have available to us, remember, is positions, distance, and stuff like. How do we get the distance? Yeah, we subtracted them. You guys remember this? We did this. We took the displacement between the two by subtracting their positions together, from each other. So specifically, I did b minus a, which means that I got a vector that went from a towards b. Like that. So I have this vector, displacement, that goes from A towards B. That has a magnitude and a direction. Do I want its magnitude?
No.
We already got it. We got it from B. Yeah. We want to move them apart in this direction, though. Whatever direction this is, we want to move them apart that direction. So we need to somehow take this displacement vector and the overlap number that we came up with and somehow combine them so that we move objects apart in this direction, but with a magnitude equal to this overlap. How can we do that? So this is what it looks like here in this case, right? That's our displacement vector. Its length is equal to d. Right? That's how we got it. That's how we got d. We actually took displacement vector, and then we used Pythagorean theorem to get the length of that vector. Right? In so many words. This could be 2 lines of code, this whole thing, but I just made it several so we could see each step. Right? But it's also going to be helpful for us to use. So we have displacement. It's the correct direction, not the correct magnitude. How do we get a vector and just get rid of its magnitude? Normalize it. Okay. And then how do we give a vector a magnitude that we want? Multiply it by the magnitude we want after it's been normalized. So we shrink it down to length 1, then we scale it by the actual number we want it to be. Great. Excellent. That's it. That's our solution. We've solved it. You know, eureka. So we need to normalize this displacement vector, and then we need to multiply that by overlap, and that's our MTV. Equals displacement. I'm gonna put the 2 bars to say, okay, no, I'm just gonna say normalized. I'm gonna pretend this is a function that exists, times overlap. Right? Where overlap is equal to this, which we already calculated. Okay? And then now we have this minimum translation vector. We have the direction and the magnitude. Then all we need to do is move by that MTV. Oh no, I put these behind. Oh, hang on. I can't grab them. Okay, here we go. Get out of here. So now we need to move them apart by that MTV vector. So I could just say like A move its position, changes position by MTV, or B changes position by MTV. What would be most reasonable though? Here, let's do some code. Here, maybe we want some code to kind of see how to get to this point. Hang on. How about that? Let us calculate this overlap. Sum of radii minus distance. Yep. That's what we did, right? Yeah, sum of radii minus distance. Then we did vector 2. MTV is going to be our displacement normalized. I actually have its length right here, so I could just divide it by distance. You know what? Maybe I'm going to do this in 2 steps. Hang on. I'm going to make a normal vector. I'm going to label it specifically A to B, because the displacement vector that I did happens to point from whatever A is to whatever B is. So I'm going to make sure I'm consistent with this. If you mix this up, you know, you forget which direction you're doing things and what signs you're dealing with, you could end up with the wrong result without noticing easily. So MTV is going to be that, but with the magnitude of overlap. Okay, so now I have this vector. That's going to be how far I need to move these circles so they don't overlap. So presumably I can put that inside this if statement. If they are overlapping, then I do something with that. You know what I'm going to do though? I'm actually going to make a copy of this function just for the purposes of showing you guys the difference between checking the overlap and dealing with it. I don't actually need 2, but I'm going to make 2. Hang on. I'm going to make 2. I will actually undo this one. I'll copy it. I'll undo this one so it remains exactly the same as we had it before. So that's circle, circle overlap. I'm going to rename this one circle, circle collision response. Okay? So this one will stay the way it is. This one's actually going to move them apart from each other. All right, so what is the difference here? It's just like 3 lines of code, which could be 1 line of code if you really wanted, I guess, but who's counting? Okay, so in here we have this MTV. Now what? If they're overlapping, then what do? We could move A plus this. Would that work? Oh, careful of the vibe thinking. Yeah, nice, good catch. Good catch. So if we did A to B, okay, and then we have this vector, it's in the direction of displacement. It's pointing from A to B. So if we just move A, it's going to be actually like super wrong. It's going to be moving it exactly the amount we need for them to be overlapping more. They're going to stick to each other.
That might be useful for other things.
Yeah, maybe. I don't know. But yeah. We could subtract the MTV. So what that would do is it would just move this exact same thing but opposite direction. So we would do that. Okay. What if I want to move both? Should I do both?
No, then they have to be
But I put them in opposite directions. So this one's gonna go like that, and then, oh,
oh, cool. Then it would have the overlap as the exact distance between them.
interesting, interesting. Okay, what if what I want is this?
And divide the distance away. You can't just divide by 2, can you? Because the radius is different.
I absolutely can divide by 2, but not up here. I figure out the MTV, and then I split it in half. So I can do half of the MTV each one gets. So that would be me splitting the difference here. Instead of moving just A or just B, that would be splitting the difference here. Each one moves a little bit. I think this is the most reasonable thing to do given the situation that we have to deal with, because if we just move one of them, then which one moves is really just based on the order inside the container that they are placed, which doesn't make a lot of sense. It's not very consistent. I think, it would not be very fair, because it would be very inconsistent. So at least this way, it's a little bit more consistent, where the order that those objects happen to be in this container, which one happens to be A and which one happens to be B, doesn't matter. Right? So let's see if this works. How can I test that? I'm going to go and find where I'm calling circle, circle overlap. And I'm just going to, for now, I'm just going to replace that with circle, circle collision response. Okay? And let me try seeing if it works based on the situation I have. Don't worry about the colors or anything like that. We still have a bug from an unsolved version of exercise 4. So don't worry about the colors. All right, let's see if they, oh, hang on. I gotta have less gravity here. Less speed. Oh, look, when we're spawning them.
Okay, but it's like
Change like size randomly.
wait.
They're not changing size randomly. I'm just spawning. But it's when I spawn them, I spawn a random size ball. If that's what you mean. Yeah.
The check's running every frame, I guess.
Yeah, every frame we're doing this collision detection and response.
But
So
now the overall, they don't turn green anymore.
yeah, that's not related.
Oh, okay.
Yeah, the not turning green is because I solved 99% of lab exercise 4, but then I left one line of code that just says return true instead of returning true or false if the half space is overlapping. Anyway. It keeps them from overlapping. That's cool. Wait, let me try a slower one, and then I'm going to shoot it with a faster one. Boom! Look at that. It says get out of the way.
But when I say it doesn't alter its like velocity or anything else.
Yes, we have not done anything with the actual momentum and making them bounce or anything like that. That takes quite a bit more math. That's lab exercise 7. This is just making them not overlap. Yes? Code? Sure. While I do that, I'm actually going to do something else, because we're going to, after we solve this, we're going to need to also do it with half spaces. So to do that with half spaces, I also need to fix lab exercise 4. Guys, here's the solution for lab exercise 4 that I didn't show before. The one with the half spaces, making half spaces detect collision. Instead of return true, I'm going to return if dot product is less than radius. I'll explain that in a minute. You very similar, very similar. Okay. All right. So hopefully this is what our work should actually look like. Here, let me show the code as well. Here's our collision response. Hopefully this is what the code. This is what result we'll get, including if the color is working correctly. Oh look, they're touching. They're just barely touching, so they turned red. Cool. Wait, can I shoot them midair? Yes, 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 yeah! Okay, we're gaming now.
Add velocity, so that way, as the gravity pulls them, they get faster.
They are.
They are.
They are. Look. We do have that. We have that. We have gravity. We have velocity.
Add impact.
We just haven't.
The ball goes and hits another ball. Then the farther the
Yes,
ball
we didn't do
hits
that.
it.
That's what we didn't do. We didn't make them actually interact with each other using mass or velocity or anything like that. So we will get some funny looking behavior, like it is kind of funny looking. So like you'll see this, right? I have a slow ball, and I'm going to shoot a fastball at the slow ball, and it looks a little weird, you know, because they just try to not overlap. That's all they're trying to do. They're not affecting each other's velocity.
It's still enough for like minimal gameplay
Look,
that needs
it's something. Yeah, it's something. It's not like it's not gonna fool anyone into into thinking you're playing Angry Birds, because it'll look really bad really quickly, but it'll janky birds.
It's kind of funny how the small ball is able to push the big one out of the way.
Yeah, we'll fix that eventually, in time. But we gotta understand this math before we can do that other math.
I feel like your half space is very disorienting.
Because he's made it like a ground. It's cool. And our half space collision works, which is nice. Like you can see that it turns red at the right time. So that's good. Right? See that? Doot, 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 doot. So this is the underside of the half space. Anything underneath the half space is colliding. Okay, great. So what do we need to do now? We need our concept of objects being solid to apply to actually all of the objects. So we needed to work with half spaces too. So this shouldn't be allowed. I shouldn't be allowed to have objects underneath this half space, because it's supposed to be solid. I shouldn't be able to shoot objects through the half space, like this. They shouldn't be able to pass through. We want it to stop here on the edge and be treated like it's a floor.
So it loses one of its features of turning red if it goes past the half space.
Yeah, you could say that.
Oh wait, it's supposed to stay red when it goes back? Oh, I thought it was like, you have to, it's only red if it's touching the line.
If it's only red and it's touching the line, you haven't made a half space, you've made a plane, basically, or a line collider. So it's a very slight difference.
So if you just want the half space to be like a floor, a physical.
It's like a floor, yeah.
And then you can't move.
Yeah.
Then just program say, hey, listen, don't go past the distance. As soon as you go negative, go back.
So let's look at the difference between the collision detection of half space and a plane, while we're on that topic, because that's a good one. Yes?
Can you like the velocity of gravity?
Sorry, say again.
Can you set it to the velocity of the gravity of like the balls from zero? Does it spawn on top of it?
Oh, yeah, we can spawn them on top of each other. This should work. It should work if you have 0 gravity. I'm being stupid and setting it with my mouse, but you guys can just set it in the code. But if you have 0 gravity and 0 speed... Uh-oh. Oh, yes, I know what this is. Yes. Okay, good point. Let's deal with that at some point later. Good point. Okay. Okay. That'll be on the list. Okay. I forgot about that. You'll notice as well, it's not deleting the objects either. Look at that.
Is that like a engine specific?
No, this is computer
I think
specific.
this is called a bug.
This is no, this is a problem with computer science that you must deal with. Yeah, you have to deal with. We must fix this. Okay, that'll go on the backlog. Thank you. I forgot about that one. Okay. So, half spaces. We want to solve collision detection and response. So, collision detection with a half space was actually this. We took the dot product of the displacement from some random ass point on the half space, honestly, some random point, towards the circle. We got like a displacement vector, and we took the dot product of that and the normal. And we got a number that's either positive, 0, or negative, based on essentially the angle between these. The angle between this distance here and that normal. Like if that was 90 degrees, it would be 0. If it was greater than 90 degrees, it would be negative. If it was less than 90 degrees, it would be positive. And the magnitude of that dot product was actually what we cared about. The magnitude of that dot product was giving us the length of this projection here. And that length is what we were using to figure out if, is what we can use to figure out if our circle overlaps. So let's do that again. Hang on. You know what? I will need a bigger example again. Yeah. I'm gonna grab this one. Yeah, let's grab this one. So this normal is here, great. Okay. Let's say our half space is our object B, whatever. Oh, you know what? I'm gonna do it the other way around. Hang on. Because I think when I did circle half space, what did I do? Oh, I didn't name them A or B. Right. I didn't name them anything. Okay. So here is our displacement. We actually had 2 of them, but we had like this. No, I'll specify that displacement. Okay. Then we had our dot product. Okay, so I'm going to copy some sample cases here because we're going to need some of these examples. So we need to be able to deal with this case. We need to be able to deal with, here, I'll make it purple. and 70% opacity. We need to be able to deal with this case. We need to be able to deal with this case. And this case. And this case. And this case. Sure. And this case. If we're working with a half space, all of these are overlapping the half space. Okay? All of these are overlapping the half space. If it's just a plane or like a line collider, then these three are the ones that are actually touching the line or overlapping the line. Okay? But I asked for a half space, so that's all these. Make sense? That's with the normal being this way.
The half space and just a plane would be treated differently in terms of collisions?
They're treated differently. Yeah. Let me show you guys the difference between half space and plane. So here, we're doing dot product is less than the radius. How does that make sense? So here's dot. Okay. In this case, what is dot product and what is radius here? Dot equals radius. Yes? Okay. If we were to also go ahead and try and calculate some kind of overlap, what would we say is the overlap here? Reasonable. Cool. What about this first case over here? Dot is... what is its relation to radius? Greater? Overlap would be negative, some negative number. Yeah, some negative number. IDK. Sure. Okay. All we know is it's negative. Actually, we know a little bit more. We know it's negative, and if that's 0, then actually it should be, we should know actually exactly what it is. Here, let me move this, adjust this a little. No. No, stop it. Okay, this thing can get a little fiddly sometimes. Okay. The overlap here will be equal to what? Okay, we can come back. It's not exactly dot. Dot what? Not negative radius. Hmm? Nice. We'll have to explain that. Yeah, we're gonna need to explain that. Okay. Let's try this again with another case. All right. What about this? What is dot and what is overlap?
Should we know? Because it's like there's no values to each thing.
You should be able to know this negative.
We'll figure out as much as we know. You don't need to have everything to have an answer. You don't know. You might have a range of numbers it can be. There is a certain range in this case where it could be. That's I haven't put numbers on it for a reason, so that we can look at it in the more the general sense. So what do we know about the dot product here?
It's overlapping a little bit.
What does that
Oh,
mean?
sorry, circle.
The variables that we have are radius, just kind of like what we did before here. We have all these basically. Oh, what did I do with it? So what are the variables we have? We have radius, we have normal, we have overlap, and we have dot. Those are the variables we're dealing with right now. The radius isn't changing here, obviously, but okay. In this case, this dot product is going to be a positive number, correct? It's a positive number. This displacement vector, you know, it's in the same direction as the normal, so it's going to be a positive number. Right? It's going to look something like this. Right? That's its displacement. You project it onto this normal, you're going to get this dot product. Okay. The scalar product, right? Scalar projection. Sorry. So it's going to be a positive number. Okay. Could it be positive anything? Could it be positive radius? Could it be the radius?
So the radius plus the overlap, but we don't know what the overlap is.
It's less than the radius.
Yeah.
Dot. We know for sure dot product less than radius.
Yeah.
That's definitely something. Okay. Is it? But we also know it's greater than 0. Okay. Okay. So we know something. All right. Now, what would the overlap be? Let's draw some more stuff. Let's see how the radius fits in this. If we draw the radius here. Something like that.
Radius minus overlap.
What? Hang on. Remember, we have dot product. We can calculate dot product. That's the variable we know already because we did it. Like, we did it here, right? We did this. We don't have overlap. But check it out. Like, this is okay. Dot product is less than radius. Okay, cool. This is where radius fits in. How do we get overlap?
Subtract the dot.
Okay. Like right there.
Oh, the radius. Oh yeah, that said makes sense.
Huh. That's exactly what worked here too. Wait, does it work in this case too? Does that work? Heck yeah, it works. They're equal. Yeah. That's pretty good.
Wait, so radius minus dot equals 0.
In this case, it equals 0, right? Because dot equals radius. Because they're the same. Cool. Okay. How about this case? What is the dot product here? The center of the circle is on the line.
So equal. Or
The dot product would be 0. It would be 0. What's the overlap? It's what? Yeah, it is.
The radius minus dot still works since dot 0.
It still works. Still works. How about this? It's kind of similar to this other case, but the dot product now, it would be a negative number. So it would look like this, but it would look like the other way around. Oh god.
So 0 over dot of the radius.
Oh god. There. Whew. Okay, struggling. So this will be negative. Dot product will be negative. How negative would dot product be? What could we say about this? So it's less than 0 for sure.
The radius plus
But what is it greater than? Greater than the dot? No. Dot is equal to dot. Or I'm asking about dot. I'm not asking about overlap yet. We need dot to figure out overlap. So we gotta figure out dot. What the dot product would be here first. Okay. Here's radius. Stick that there. Please bear with me. There we go. So you could say that its absolute value of the dot product is less than the radius in this case. No? Yeah? So the dot product isn't, it's less than 0, but it isn't less than negative radius. Maybe I could say it like that. Yeah. Okay. If we got numbers outside of that range, then we should be concerned, right? That's what. Anyway, okay. So overlap in this case, will it work? Let's try it. Radius minus dot product. What is our overlap? Radius minus dot. Huh. So are we gonna get a positive number or a negative number or what? Dot product is negative at this point. Radius is positive. Dot product is negative.
just make it positive as a calculation.
No. No. That would actually mess it up really badly. You don't just make it positive for no reason. Guys, don't pick to subtract numbers. Oh, I'm going to subtract the smaller number from the bigger number. Don't do that. Never do that. In like the computer science and stuff like that, when we're doing this kind of math, you need to care about the direction. So don't always just pick based on which one's smaller and which one's bigger or something like that. Be careful of doing that, because if you're not careful, then you don't know why you did that, and then you need to be consistent with it, whatever you do, right? So the reason I subtracted, B minus A is just because I wanted to think about it consistently as A towards B, whatever A is, I don't care. But as long as I can stay consistent, right? I wouldn't be able to change the order of this randomly. It would not work. I couldn't just say, oh, if distance is greater than sum of radii, I'll subtract the other way around. No, we don't want to do that. So what happens if we just, let's work with what we came up with. What happens if we end up with this? Radius minus dot. What are we going to get? Dot product is negative at this point.
But the radius is greater than the dot product, so we shouldn't end up with a negative number.
So, hang on, no. It's minus a negative number. So we're just adding. So let's add. Let's just put these two together. This is what we'll get. If if we're subtracting a negative number, we're just going to add them, and this is what our overlap is going to look like. Is this overlap correct?
No.
Wait. What?
Oh, for the half. Oh, yeah. Okay. Yeah, because it's the half space.
Yeah, huh. Let's move this up by the overlap, see if it gets us where we need to go. So it does. Okay, how about this case? What is dot product here?
Also negative.
Definitely negative.
And still not less than the radius.
Negative radius.
It would be negative radius. On point, dude. Crazy. It's the same as this. Here's our dot product. Oh, damn it. Damn it. Come on. No. Okay. Same. Overlap. What would it be? Yeah, what if we do radius minus dot? What are we going to end up with? Nope.
The full.
Because dot product is negative. That's why we wouldn't get 0.
Double the radius.
Overlap was 0 here when we did radius minus dot, but dot product was positive. Right? Radius 5, dot product 5, subtract, you get 0. Here, it would be more like radius is 5, dot product is negative 5. Then if you do 5 minus negative 5, you'd end up with what? 10. So actually in this case, overlap would be equal to 2 times the radius. Which is the same as radius minus dot, whatever. Okay, and then one more case. All right, one more case. So our overlap here, dot product here. Hang on. I'm just eyeballing it, you know. But it's good enough, actually. It seems to be good enough, eyeballing it for now. Radius, thankfully I don't have to change the length of that every time because I use the same circle. Okay. What do we know about the dot product in this case here? This is the last case, guys.
Negative and radius.
It's definitely negative, yes.
The absolute value is bigger than the radius.
Yeah, it's more negative than even negative radius would be. Yeah, so, you know, the... Great. Did I do that right? Hold on. No, I did that wrong. Hang on. Dot is less than negative radius. Yeah, there we go. And overlap, again, if we were to apply that, if we were to do radius minus dot product, okay, that would be my overlap, okay. Let's do it, moment of truth. So I take the center here, and then I'll move it to the top of the center of this overlap. Yes.
Oh my god.
It is complete. We did all the math.
The prophecy has been fulfilled.
There is no more case. We have seen every possibility. How many of them did we win?
All I do is
So for all of these, the one little equation, radius minus dot product, worked great. Actually, what did we do for this one? How do we calculate our overlap? Radius minus distance. Same thing, almost. Right? So our dot product actually is really our distance. And then the sign tells us which side we're on. If you just take the absolute value of the dot product, you will get distance from a line. And so here, the dot product would be, you know, if you just took the absolute value, right? Then look at these three cases. These are the three cases where these three cases. These are the three cases where the absolute value of the dot product is less than the radius. So if you wanted to do line collision instead of half space collision, all you'd have to do is check the absolute value of the dot product. So the difference between having a half space and having a line here for collision detection would be as simple as, where is it? Circle half space, yeah. Instead of dot, absolute value of dot. Let me test this one. So now this is no longer half space, it's a plane, or it's a line. Hey, look at that. Yeah, you did it wrong, but it's fine. You didn't do what it asked. The assignments did tell you, it did specify the differences between them. But hey, you know, it's close. Isn't that pretty cool though? I'll leave this alone like that. Okay. Similar to what we did with the collision response for the circles, I'm going to take this and just copy it again, just so you guys can see the comparison. I don't really need both, but I'm going to have both anyway, just so you can see the difference. So you're allowed to have them return the same thing and take the same thing, but you can't have them also have the same name. I'm going to get rid of a bunch of the comments for this one though. Okay. So now let's do and you know what? I'm going to comment out these as well. The drawing stuff. We don't just want to return straight away. Now we want to actually have some collision response. So hang on a sec. If then do something else, return false. Okay, so if they are overlapping, then we do something, and we also return true. Cool. So let's figure out overlap. Oh, by the way, with this circle, I didn't need to do all of this here. I could do this only if that is true. Actually, another way I could do it is I could figure out overlap and then say if overlap is greater than 0. See that? Because when is overlap going to be greater than 0? When this number is bigger than this number. Right? That's when this will be greater than 0. Technically speaking, this will be, you know, a little less instructions, so it could be better. I feel it looks pretty clean. I like the way that it looks. That's the most important part. Actually, helps reduce bugs. I like the idea of overlap, meaning if it's positive, you're overlapping. If it's negative, you're not overlapping. Right? If it's 0, you're on the edge. Makes sense to me. We can do the same thing here. What was our overlap? Radius minus dot product. Circle dot radius minus dot. So then if overlap is greater than 0, and again, when is this going to be greater than 0? When this number is bigger than this number. So when this number is bigger than this number. Yeah. Cool. So we have our overlap. We have our magnitude of how far we want to move these things. Only thing that we're missing now is what direction. Can you guys think of a reasonable direction for us to push these objects? Should I move the half space? No.
Can you use the normal?
Yeah, use the normal. I'll move it along the normal. We already established that this normal is going to be the shortest direction. Like it's the only direction that matters for this collision, right? So it's totally reasonable. Yeah, move it along the normal. Let's make our MTV half space normal, get normal times overlap. Okay. And then we don't need to move both, we can just move the circle. Are we moving it in the correct way if I just do this? Is this correct?
They'll show to multiply by 0.5.
No. The reason we multiplied by 0.5 with circle was because we moved both circles. If I'm just moving the circle when dealing with circle half space collision, I'm not going to multiply by half. It's going to get the whole MTV. So whatever this overlap is, only the circle is covering that distance. Is this correct? Half space normal points up this way. The dot product, based on the way I did it, the dot product is positive when they're on this side, because I did displacement from plane to circle. If you did this the other way around, everything would be flipped. You can still do it flipped. You just need to know that you did it flipped. So if I did this the other way around, this displacement vector would be negative when I'm outside, like this, and it would be positive when I'm inside instead. That's all. I mean the dot product of it. That's what I meant. Sorry. But what I did was from the plane to the circle, and then I tried to make sure that I kept consistent with my directions. So is this good? Yeah. Yeah, hopefully. Hopefully. Let's try it. Okay. I'm going to replace these lines of code here. And we'll run it and see if it works. Okay, if I spawn something, what do we want to happen if I hit spacebar right now?
It should go above the line.
Should instantly teleport up here. Okay. Oh, it did.
And it...
Yeah. Yeah, it's... Don't worry about the velocity. Don't worry about that. Let's just...
Make them fall. Twitch the...
Oh, move this? Yeah. It's like one of those satisfying videos. This is so silly. It's so stupid, but.
Whoa.
Oh yeah. Are you satisfied with this?
Are you satisfied with your service?
They're still building up velocity. You can see the velocity vector is getting bigger and bigger.
So if you were to like drop them, would they all just sink in the air?
They're sinking faster than you might expect, right?
Kind of just like slide off it and they don't really bounce.
Yeah, they don't. There's no bouncing code or anything like that, and there's nothing changing their velocities right now, right? So actually, gravity is still applying to these, and they're just gaining greater and greater and greater velocity in the negative direction, or like in the downward direction. They're getting faster and faster, but the half space just won't allow them to go through. Oh, you know what? This is a great opportunity. Let me show you guys what happens if instead of a half space, I were to make this do something funny. Let's see if we did this. Yeah, let's try that. See what happens. Let's take the absolute value of the dot product. Let's see what happens. Oh, doesn't work. Oh, but it does. It's not that it doesn't work, it's just change it to work for lines instead. And it's not that great at it. It always pops them out actually on the positive side. We've actually created a, well, I guess you could want this. This could be desired behavior. It's like a one-way gate. It's kind of neat. Look. Whoop. Interesting. It's not 100% correct, actually. But also, something else funny happens. Eventually, these objects, they'll build enough velocity. They just fall straight through. They just teleport through, actually. Because one frame they're up here, next frame they're not even touching the line anymore. So we have no way to defend against that.
Johnny, are you trying to do a raid?
Anyway, half space avoids this problem of tunneling, where objects can just pop through the floor. Okay, and that's actually pretty much it. So here's what I'll do now. I'll pause the recording, and yeah, let's try and get it done. I want you guys to finish it. Can we finish it? Let's finish it. Or if you need help on something else, I'll help you on something else. Okay? We still got a good 20 minutes at least. Cool. Lab exercise. Okay, there's one more thing I need you guys to do, but I wanted to pause and have a look first. The thing I needed you guys to do is make a bunch of planes rotated at different angles or half space. Actually, sorry, I wanted half space. And I want you to drop a bunch of spheres onto it, or balls onto it, circles. So I basically want you to make it like a little bowl, and then I want you to drop them onto the bowl. Okay, if you guys want to see that before I pause, I'll do that. You want to see that right now? Okay, alright. Okay. Okay.
Yeah.
I'm gonna make another half space. Okay, 2. Electric Boogaloo. Half space 2. Let's add the second half space to the world. Let's make it not like use that gravity stuff and whatever. Let's give it a position. Okay, hang on. I need to give both of these a reasonable position. Hang on. 900. 200? 600? 900? Okay, and I'm gonna give them rotations to start with. set rotation degrees. I have a function for that, great. Maybe that one's at negative 10 degrees, and then this one at positive 10 degrees. And then I'm going to add the reference of this half space because it is a physics object. I'm going to add it to the world, and then let's see what we get. That's not exactly what I wanted. I wanted them to be a little bit further to the right maybe, but it's something. So now I have two. It's like a little bowl.
Oh.
Spin 'em. They're fighting because there's a bunch of them like trying to push each other apart, and because their velocities are getting really big, and then they're getting teleported back up here. All sorts of stuff is going on at once. Woof.
Fine.
Remember that gravity is really strong. Let me turn the gravity down. Well, let's turn speed down. There we go. Remember, you don't have to have anything dealing with velocity. If you want, you can add something to, you know, stop them from growing like crazy if you want. Look at that, I can scoop them up. I can pick them up and I can scoop them. And this, since the rotation point is actually set by this position, I can kind of like do this. And then, woo, oh, okay, bye-bye. Okay. This is fun. Ooh, okay. And the collision with the circles, it's pretty consistent as well. Oh yeah, it gets a little iffy when there's a whole bunch of them, because it's not super stable when that happens. Don't worry about that. That's okay. That's okay. 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 There is actually some other problem. Thank you for bringing it up. There's one more problem. If I start my objects in the exact same position, I have some problems, actually. There are some problems with that. So hang on, let me deal with that. Also, let me start pause. 100, screen height 100. Let's do the start position a little higher. Yeah. Okay. If I begin with the speed, where's my speed variable? Speed 0. Gravity, where's gravity? It's inside my physics world. Gravity 0. We make very bad things happen if I spawn objects like this. Oh, actually that's, thankfully these half spaces are actually solving it for me. Hang on a second. No, that's not good enough. Hang on. Screen height minus 800. Okay. Oh. Oh, wait a minute. Sorry. Start, pause. Oh, whoops. I did a bad. Oh, okay. I did it bad, and I put this in a separate place from where I actually shoot the things. So when I shoot them, I'm doing something like yeah. I shouldn't have done it like that, but there's draw, and then there's, here we go. Height minus 800. Actually, let me just put start pause somewhere else. Okay, let me just define start pause like up here. Yeah. $100 get screen. Let's do 500. And then on start I can do get screen height minus, I don't know, 500. All right, let's try that again. So I think my start position, okay, it's over here. So if I started at speed of 0, I spawn 2 objects, they kind of go away. Something very spooky happens. Actually, yeah, it's really
But
spooky.
If the object counts as adding an input,
They're in here somewhere.
that's
They're all in here somewhere. Let me debug for you guys. Let me show you guys what's going on with these objects' positions. This is still running. I'm gonna go place a breakpoint in the draw. Let's see what's going on with some of these objects. Okay, let's look at the values inside this container. Add watch. I right clicked and I hit add watch. Oops. I want this down here. Okay. Let's read the values associated with these. Okay, so these are circles. So these are the half spaces, clearly. These are the circles, radius 20. Okay, sure, whatever. Okay, what's its position? Nan? Nan? Do you guys know what nan is? Not a number, not bread. Not the bread. It's not a number, but there's a lot of nan here. Look, these are all nan. There's more nan than on all of Brampton. Very nan. Where did that come from? How did we get it? Yes.
I was like, so it's because it's you get divide by 0.
Yes, we get a divide by 0 somewhere. Nan, or not a number, can happen when you divide by 0, because the answer to that is undefined. The answer to that is not a number. Where could we have been dividing by 0 when we're spawning objects directly on top of each other? It has to be somewhere.
because they're right on top of each other, so the distance between 0.
Oh, yeah? Okay, where does that matter?
In the relation.
Yeah, so we're doing displacement. Okay, displacement, we get a 0 vector. Distance is going to be length of a 0 vector. That's going to be 0. Oh yeah, it's right here. This is the culprit. Let me put a breakpoint here and let's watch it happen in real time. So I'm going to spawn an object. Okay, great. Spawn another object. Now it's hit this breakpoint. There's 2 objects in the world. Okay. Displacement is 0. Uh-oh. Distance is 0. Everything is fine for now until we do this. Then we get, this is, normal vector is not a number. And nan is like infectious. When you do any math with nan, you get more nan. Okay? It's like it multiplies itself. So now this is, the components of this vector is not a number and not a number. Then when we try to multiply it with overlap, which is like a valid number, the answer that we get for MTV is not a number and not a number. Then we try to say position minus equals and position plus equals. This position is normal, this is fine. Then we try to subtract not a number from it. And we get not a number, not a number. So that's how this happens.
Are these still visible somewhere?
No, they're not visible anywhere because the draw function doesn't know how to draw something at not a number pixel position. So they are not anywhere. It is not a number. It's not even infinity. Infinity is a value that a floating point value can take, which you don't really want either. But infinity and negative infinity are values that a floating point number can have. Not a number is another one, but not a number is the worst. You can't do anything with it. Yes. Good question. Can you check if something is not a number? There's a function called isNan. That's the only way to check if something's not a number without ending up with not a number. You can't check like less than or greater than or anything like that. None of those work. You actually can't even do is not a number equal to not a number. That's not even allowed. You actually cannot do, bool or you can't check something like you can't do something like that. You can't. You actually have to do isNan. Anyway, we're gonna avoid having nan anyway. We don't want nan. How can we do that? So in this case, when they're directly on top of each other, what do we want to do? You could just say do nothing, I guess. But I mean, yeah, I guess. Yes?
I just made it so it's
How about this? If they're directly on top of each other, our normalized vector, because that's what we need. This distance is 0. Okay, we get our normal vector. Let's just make it up. Whatever. If distance is like 0 or really small, so you could say if abs of distance is less than like a small number. There's numbers you can use for this, but I'm just going to do that. Then the normal is going to be 0, 1. Hang on. I think that'll be okay. Let's see if this works. Yeah, that's good enough for me. So if they're directly on top of each other, it'll just decide to move them up and down vertically. Woo! Okay, job's done. All right, guys. So that's what we want. We want to have this, and we want to be able to drop them into a little fruit bowl or something. Okay? Don't worry about that. That's fine. There's too many. It should be stable with like a few of them. But once you start getting balls on top of balls on top of balls, then it gets a bit weird. Okay? But otherwise, it should be good. Any other questions? Have fun with it. Enjoy. Yeah.
So this lab where we have to get the balls to physically touch each other.
Yep.
That's due November 9th.
It's due whenever it's due. I think so. I think so. I believe so, yeah. Yeah. We just solved the whole thing just now.
I know, that's great.
Yeah. There's nothing else to do about it except, you know, if you want to, except adding more controls to fiddle with it and stuff like
You
that.
have to do the whole thing, right?
Yeah, make a multiple planes and stuff. Okay, thank you very much. That's it for now. I'll see you guys next week.